second talk. So we are very fortunate to have Professor Márcio Catelan visiting us this and next week. So he is part of this downlab visitor program everyone probably has heard. So Professor Márcio Catelan will be here this and next week visiting us, and his office is at AB 123 in case you want to talk to him after this talk or for the rest of the week and next week. I'll give a brief introduction for Márcio. So Márcio was originally born in Brazil, I believe, but did his PhD in Chile. Also in Brazil. Sao Paulo. Sorry, somehow I thought Sao Paulo was in Chile. That's a big mistake. Yeah, at the University of Sao Paulo. And then I did his postdoc actually in US, I believe. And I could be wrong, but I think you probably the first Hubble Fellow that from a Hubble Fellow with a PhD in Latin America.
That's correct.
That's probably the case. So at that time, in early 90s, when Hubble Fellow was not that, I mean, it's still prestigious nowadays, I guess, but nowadays there's so many postdoc fellowship. Everyone will hear one or the other, but in the early 90s or late 90s, that's one of the very few postdoc fellowships. So yeah, Márcio got one of those. And then he moved to Chile for his first position at the Universidad, Catholic University of Chile. And I think Márcio is both a theorist and an observer, I would say, and worked on both stars and galactic astrophysics. And as you may know about the ramping up of the LSST going to come online, so you will hear a lot of things about the activities in time domain survey that in Chile, and some of those will be highlighted by Márcio in his talk today. So it's supposed to be a highlight overview talk, and as also the advertisement show more detailed talk later for CETA talk later, I think on Thursday. So with that, I'll let Márcio take over and tell us about the time domain activities in Chile. Thanks.
Thank you very much. So glad to be here.
Is it okay to be on this side because the microphone is here if we want online to hear? So that's the
I'm the kind of guy.
Sorry, yeah. We should give it.
Okay, so I'm gonna tell you about time domain science. Some things we've been doing from Chile. I'll also try to give you an overview as an introduction to the talk that you will see on Thursday. So,
just put it on once.
Right, so variability in the universe is a very complex thing, right? Variability manifests itself in many. I'm generally interested in stellar variability, and so I'll show you here the variability tree that was put together by the deity on occasion of the second day of the year. And you can see how complex it can be, divided into many sub-branches. I've done some work on several of these different branches, but most of my work focused over the years on pulsation. I work mostly with pulsating stars. In the case of pulsating stars, over the years, we've come to develop a very good understanding of different ways in which stars pulsate. They can pulsate radially, not radially, in different modes simultaneously, and also the excitation mechanisms that drive those pulsations. So you've probably heard the term instability strip many times. This figure here, by Jeffrey and Side, shows that there's not one instability strip, but there are actually many instability strips across the diagram. And the one that we normally refer to as the instability strip is the classical one that's actually right here, where we find stuff hits on water stars, galaxies, and light. So to get to this level of complexity in our knowledge, a long time has passed, and many people over the years, decades, if not centuries, have scanned the sky more or less systematically, acquiring data and developing taxonomies that eventually would come to interpret in terms of physical fields. So I want to show you this plot I gathered in my recent stars as a function of time. And you can see that there's tremendous progress, on variables, culminating with these three, where we have reached something like 10 billion known variable stars in the universe sky. With LHC that's coming out, we may infer that it's undergoing commissioning. The commissioning with the commissioning camera that's passed in flying colors, so we're all very optimistic. LHC will live up to its promise, and that it should be able to find more than 10 to the 8 variables, which is a huge amount of data. I mentioned the pioneers not just because it's an interesting, it's an interesting story of interest, but also because the data required in terms of photographic plates, they actually hold very important information that we can harvest and use for astrophysical applications that wouldn't be possible without such data. And we owe great gratitude to Washington Harvard that has been scanning these plates from the Harvard collection for many years now. They just put out their final data release in late December. And I'll show you an example of what we're saying, how these data can be useful. I show a project that we conducted with some of my students. But we undertook the task of measuring the period change rates of subfields in the large magnetic. That's basically a measurement of how the period of the star is changing over time. The periods of the stars change over time because they evolve. They're traveling in probably even though we are not able to see that in our life. Pulsating stars offer us a technique to actually detect that kind of motion appropriately. Because the stars are crossing the HR diagram, they're changing their density, and by changing their density, it also changes their periods. And we can only measure that with data spanning a long time. So we did this for many studies in the galaxy. So here's an example of a study incorporating data from forms. So assuming that 32 days, not yet in phase of light, but we can actually measure the definition phase as a function of time when the observations were taken. And when we do this, we see that there's not a random plot, but actually a line, double points. This nice quadratic line implies over C vector means the definition position of the vector with respect to what you would have expected for this period, if this period counts. Right? So clearly the period is changing over time. If we take that into account and phase the vector, we get a much better phase, like what's the story over here. Some dispersion is to be expected. But we believe that we did this for over 1,300 stars in galaxies. This is the biggest sample in any galaxy, including ever. So we compared that with models as well. Before I show you the models, let me just tell you what we expect. So this is the evolution of quarks of a star, and the star crosses the history of these three times. So the first time over here, second time over here, and third time to the AGE. The fundamental equation of stellar pulsation theory says the period should go inversely as the square root of the mean density of the star. Therefore, if the density is increasing, the period should be decreasing, and if it's decreasing, the field should be. So the first crossing we expect positive phase rates. The second crossing we expect negative phase rates. And immediately though, we determine those rates and find exactly. We find lots of stars that are so they are the second crossing, and there are many stars in the third crossing, meaning they're on the blue loop. We basically don't find almost anything on the first crossing because this is the original graph of stellar evolution, which is well known as a very fast evolutionary phase where we basically don't see stars. Right? It's so big that it's very hard to see. However, close attention, we actually did find stars up here, consistent with the first crossing. We are pretty sure that we detected two stars crossing the Richmond Gap on the way branch, and the piercing rates are very trustworthy because they are large, so we could measure them very quickly. See here, comparing the previous slide I showed you, the piercing rate we used so we are pretty confident that we detected some of the first Sapphire's crossing the first crossing. So we compare this with theoretical models. So see what the theoretical evolutionary tracks or unique star, the rotation rates, different as well. And so for these stars, you would expect that these two first rising stars, you would expect here. So we use MESA for that. I also want to tell you that we have Católica, or almost stellar evolution club, it's a 3D program. It was developed initially by Martin Schwarzschild and by Alan Spiker. I was Alan Spiker's postdoc, and my second was to update. So with each book, we're just about to publish the most extensive grade of horizontal branch stellar evolution models in the literature, wide range of methods, and alphabetical enhancements that will be available. So each book is especially tailored to deal with low mass stars. And our light stars are low mass stars as opposed to Cepheids, which are totally four classes of Cepheids, which are intermediate. So we did the same kind of analysis, whole mass diagram, trying to find bigger changes with our light stars, and we found cases like this one. So this here is phase light curve. You can see here that the phase light curve kind of goes back. This oscillation is caused by binarity. We believe we've detected the binary thing, and what we are seeing is the light travel time effect. Basically, when the RLA is farther from us, the light takes longer to arrive. When the RLA is closer to us in the orbit, the light arrives sooner. And we are actually able to measure this. And when we do the overall it's even on the curve that we can model the binary codes. And by doing this, we are able to get constraints on the masses of the head. So this number star and mass that we find things. This is the first ever population study of binary RLA stars in the literature. Until just 10 years ago, it was just one binary RLA star. So we believe that white dwarfs that make these stars, substar objects, brown dwarfs and such, and there may be M dwarfs. We don't see them, they're extremely faint at the contrast with their orbits are very long, huge. So detecting those irregularities is a major challenge. We're trying to do from. One thing that you can do with the stars as well is a bit of electric cosmology by trying to compare the properties, in this case, the average periods of maybe type of light stars. So this one, the average periods of those stars, the velocity for Milky Way clusters and logical clusters and more star galaxies. You'll see that the contrast, right? There's a gap in clusters, and there's not such a gap on the country in nearby external up. So this difference led me to play years ago not the disassembly of the issue of galaxies with present day. By the present day, satellites I was talking about, the satellites were around in 2009. The field has exploded in more recent years, so the situation has become much more complex, but still, it's guiding much of the research that's being done nowadays, searching for the kind of fragments that can effectively and contributed to the volume of the Milky Way, reducing therefore. One major reason why pulsating stars are used in astrophysics is that they are good distance indicators. This is probably the most comprehensive period of observation you will ever see for pulsating stars. It goes all the way down to the stars and rises all the way to the top. You can see the different subclasses of pulsating stars follow different relations that are extremely important because you know the absolute magnitude of the star, and thus if you know magnitude of the star, its distance, you can trace distances all around Milky Way. In the case of our stars, you can see that the relation is not supported by we explained this a few years ago by some branch as a function of the aspect study. Blue, visual, infrared. You can see that the visual, the horizontal branch is flat. It's horizontal. That's why it's called horizontal branch. Well, the stars are easy because the pioneers observed its horizontal thing. However, the horizontal branch is not horizontal bend. And as you go towards near infrared, things start getting much nicer in terms of applications because you start having your light stars covering a wide range of absolute magnitude. So this is what you can see here. So in UVR, I, J, H, and K, you can see how exquisite the relation becomes actually reaches at the end. So this has been used quite extensively in recent years in studies of light stars in the Milky Way bulge. I've carried on lots of I still have five. So we've been using these period luminosity relations and period, temporal magnitude minimalistic relations for light stars to trace structures over the Milky Way. These are some of the first studies where such structures detected. We've done a long way since those early years. Our light stars have tracing structures such as helium. For instance, in the case of Alfred and Taylor, Sandy Cooksoft and the maintained as well a few years ago showed using our light stars that the north and south components are actually connected. So they're part of these strings. Going further up in the field, there's very much work being conducted here in Toronto. Is surveying detecting light stars that are really very far away. This is being confirmed by other studies as well. Now, going to the inner galaxy, we have a major problem, which is extinction. Right? So this is what you invisible. We go to the near infrared. This is two mass, and you can see that stars suddenly pop up. because extinction is much reduced. So this is the same. So for this reason, we've conducted over the past 15 years the VPP survey with extension X. This was a deep time series multi-band survey of the galactic bulge and inner disk in the near infrared with much higher resolution as well as the two. So with this, we could for the first time use variable stars to penetrate the stars of dust in the inner Milky Way and probe the structure of and even the spiral arms beyond. Using this is one result that were some of these was the tracing by detection of classical symbols trace the extension of some of the local spiral arms to regions that have been hidden from us because of having extinction. My student, Daniel did some of the same kind, so we separated and pointed out that the warming depends, warming is inclination at the edges. This depends on latitude, confirming previous studies, but now in regions that are not surveyed extensively before. We also have evidence of flaring in the sense that this the scale is quite significant, and also the direction age. That's not the case with our other stars and type 2 Cepheids. Those two are ancient stars as opposed to the classical Cepheids that are fairly young. So in those cases, they have to follow a traversial and ellipsoid tracing. So looking to the future, we have LSST coming up, and LSST is going to be producing Kubernetes of data flow 50 terabytes per night, was that seeded in the amount of data is really amazing. It will be a multi-filter, 6-filter survey to handle this kind of data. We need automated techniques. This is why the Wood Observatory put together the alert brokers. There are several alert brokers officially in place. Alerts is one of them. Alerts is the one that we have to ship. So this is the paper presenting this broker. So the goal of the broker is to ingest the alert stream from the observatory. Now we're CTF, soon we'll be LSST and LS4. We ingest the alert from the observatory, we classify the source as to its variability class, and we put the results at disposal. We have several layers, several techniques for this project. This is the web page to explore the University Explorer, the Milky Way. This is the army of students and postdocs that are working with this project. Some of them are very good samples from the analysis of light that are often this one that you cannot make sense of. This is the best showing in black or so far, and the other is in color. Students represent a description of the black.
A lot of content in 20 minutes, I think, ranging from stars to galaxy, from the boat to the halo to different surveys. But any questions for Márcio? Or start with Martin?
You other fields, we have different crossings. If you go back to that, the theoretical models didn't seem to match that. They matched really well in some sense, but they didn't quite go to left them out on the panel. What's it model with the side area?
That's probably the third crossing.
If you're not even fair. It's not that very.
Yes, yes.
It's very good.
Oh, good question.
Oh, the-
Sorry.
No, no. Yeah, I have your screen shared. Yeah, the screen share is working.
It's too small.
Okay, now it works.
Yes. So you're probably referring to this, yeah, that guy, also a little bit on the science posting, it doesn't seem quite aligned. That's.
Yes, I can tell you what's happening. Producing satellites at this position where it's is not trivial. Press from mass to low mass. We come here and you see that the movements not reaching the experience level. So this is a known problem. Right. It's a problem that's there. The solution to this may have to do with two the compaction factors or to the mass loss taking place at the stuff. Okay, so these are theories that have
80,000 space revolutions.
lead there. One thing that improves it is but it still doesn't fully solve it. Thank you.